All right, this is chapter 5 on volcanoes, and we will be starting this first section on magma. Magma comes from the mantle, and once it comes out to the surface, we call it lava, which gets confusing. I don't know why we have to differentiate the two, but we do. And magma sources about 50 to 250 kilometers deep. And that is where the temperature is high enough and the pressure is low enough to melt rock. Because as you go deeper towards the core, the pressure increases so much that things solidify again, even though it's still super hot. So there are different types of magmas. Out of the way. And it really comes down to we kind of measure it based on key ingredients, being silica and iron and magnesium. So if it's high in silica, we call it felsic. And if it's low in silica and high in iron and magnesium, we call it mafic. Usually it's like two ends of the spectrum. You don't usually find a high silica and a high magnesium and iron. It's kind of like an either or a range in between. So if we come down here, we have our ultramafic, which has a lot of the ferromagnesium, which is the iron, and the magnesium. So ferro is like iron, like Fe on the periodic table. Ferromagnesiums. And then quartz, here we have a lot of that's the silica base, so the felsic. So this is going from felsic to ultramafic. Ultramafic just means like uber rich in these ferromagnesium minerals. And so we have basic rock types. These are our extrusives here. We have rhyolite and basalt. Andesite's kind of in the middle. And then if it's intrusive, which I don't know if we've talked about this or not, but if we haven't, we'll get there. If it's intrusive, meaning it's cooled within the crust, extrusive is if it comes to the surface in a volcano. Their rock type equivalent of rhyolite is granite, and the equivalent of basalt, if it cools within the crust, is gabbro. So it has that same range. Okay. And based on that, it behaves differently. And so viscosity is the resistance to flow. So, like honey is more viscous than water. And silica rich lavas are more viscous than mafic lavas. You can think of silica as kind of like a thickening agent, if you will, like flour in your pancake mix. And trapped gases can have an effect too, and if they get trapped, they can cause explosive eruptions. And you usually find the trapped gases in the more viscous, silica-rich types. If you think it's easier to like see those little air bubbles in your honey than it is to see little air bubbles in water. And if they are in water, they just come right up to the surface real quick, right? So same kind of thing. So the more viscous lavas can trap the gases more easily, and then they can be more dangerous. If you remember, the silica comes from your granites and things. So you'll find these more dangerous explosive types of volcanoes where you're getting more of the continental crust melting than if you were getting more of the asthenosphere or oceanic crust melting and turning into lava. And then as things, so if they melt, it's usually temperature and pressure, right? Temperature and pressure. But different minerals have different melting points. Just like how, adding salt to your ice road in the wintertime lowers that freezing point. It's like the same concept. So different elements and different minerals will melt at different times. And so you can get partial melting. And this is when certain minerals melt and others don't. And so then you'll end up with like two different rocks kind of next to each. Let's say that the melted part resolidifies. You'll have two different types of rocks. You can end up with two different types of magmas too because of this. So it can get really complicated. That leads to fractional crystallization, which is same thing. It's like instead of the melting point, it's like the freezing point where as things are cooling, certain crystals will form out of the solution before other ones will. So that, I guess that's all you really need to know. Material to mix with, I don't know. Decompression melting due to, okay, so this is decompression melting is when you reduce pressure, and I really wish I could like use my hands, but this system won't let me do a video recording and screen and audio at the same time. If you reduce the pressure on something, you can actually change its state. So it can go from a liquid to a gas or a solid to a liquid. You can actually in the lab, like take a beaker of water and put it in like this device that sucks the air out and reduces the pressure, and that water will start to boil even though you haven't added any temperature. And so rocks can melt as they come towards the surface in like that rift zone just because of the reduction in pressure, not because of heat. And then this is just when crustal material kind of gets mixed in like on the sides of a magma chamber. I don't think that's that important to know. Magma differentiation. So this is, we talked about differentiation when we talked about the beginning of the planet and the solar system. Same thing. So if you have this magma chamber and everything's molten, then you're going to have the denser minerals settle down at the bottom and the lighter ones on top. So you'll get the ferromagnesium minerals down at the bottom and the silica and the granite. So granite and rhyolite up here and more basalt down here. Then where do we find magma? We find it at the divergent plate boundaries. So there is not a picture of that here. But over here where there's the divergent plate boundary, that is that decompression melting. Things are coming up, so they're melting, then they cool because they're on the surface. We find them over subduction zones. Again, that is because of this water from subducting crust. So this is all ocean, right? So it's wet. And then the water gets hot enough, the water vaporizes. And then that steam is what actually heats all of this above it. And so up here we have that, crustal material full of silica, so we can get some of those explosive, dangerous types of volcanoes right here. And then we find them at hotspots, which are also out here in the ocean, and those comes from the asthenosphere or the mantle. And so they usually, if they're in the ocean, like Hawaii, they don't have the silica explosive types of volcanoes. Now, however, we do have over here, if this is the coast of California anyway, so then we would have Hawaii hotspot, we'd have the Yellowstone hotspot. Now that is over the continental crust and can be very dangerous. And it actually trends from it starts out really dangerous as it depletes all of the silica and then kind of gets down lower to those deeper chambers, and then it becomes less dangerous and more of that basaltic flow. And that's what we see at Mammoth. When we look at the super volcano at Mammoth in California, that we see a lot of historical basalt flows from that. Although Mammoth, I think, is a rift zone and not a super volcano. But Mammoth is going to come up later, which is why my mind went to that. So that is that for magma.